Continuity and one-sided limits. The goal for this lesson is to help you determine continuity at a point and continuity on an open interval. It will also help you determine one-sided limits and continuity on a closed interval, use the properties of continuity, and understand and use the intermediate value theorem. Let's begin by discussing continuity at a point on an open interval. In mathematics, the term continuous has much the same meaning as it has in everyday usage. Informally, to say that a function f is continuous at a point C means there is no interruption in the graph of f at C. That is, the graph is unbroken at C and there are no holes, jumps, or gaps. This figure here identifies three values of x at which the graph of f is not continuous. On this first case here, this is an example wherein the function is not defined at x equals c. So in the graph, there's a hole at x equals c. On the second case, the second example here, is the instance wherein the limit of the function as x approaches c does not exist. As you see here, you have a graph. So on the left side of c, this is the graph of the function, and on the right side of c, the graph of the function is this. So in this case, the limit from the left is different from the limit from the right. Therefore, the limit does not exist at x equals c. On the third example, this is a case when the function is defined at x equals c, that is equal to this point here. But when you take the limit of the function as x approaches c, that value is not the same as what you get when you evaluate the function at c. In all other points on the open interval, the function is continuous. So from the previous slide, we've seen that continuity at x equals c can be destroyed by any one of the following conditions. First, that is when the function is not defined at x equals c. That means when there's like a hole on the graph. Second, when the limit of the function f of x does not exist at x equals c, when there's like a break. And third, when the limit of the function exists at x equals c, but it is not equal to f of c. This is when you have like a hole, and then there's a point at on the other parts of the graph. Now, if none of the three conditions is true, the function f is called continuous at c, as indicated in the following important definition. Now we say that a function f is continuous at point C when all these three conditions are met. First condition is when the function is defined at C. Second is the limit of the function as x approaches C should exist. When you say that the limit of the function as x approaches c exists, that means that the limit from the left of c should be equal to the limit from the right of c, or the left-hand limit must be equal to the right-hand limit. Now, third, the limit of the function f of x as x approaches c is equal to the value of the function evaluated at c. In this case, if all these three conditions are satisfied, we say that the function is continuous at the point c. Now, let's define continuity on an open interval. A function is continuous on an open interval when the function is continuous at each point in the interval. And also, a function is continuous on the entire real number line And that is everywhere, we say that that is everywhere continuous if it is continuous from negative infinity to positive infinity. Now let's consider an open interval I that contains a real number c. If a function f is defined on that interval, except possibly at c, and f is not continuous at c, then f is said to have a discontinuity at c. Now, discontinuities fall into two categories. First category is what we call a removable discontinuity, and the second one is called a non-removable discontinuity. A discontinuity at C is called removable when f can be made continuous by appropriately defining or redefining f of C. For instance, the functions shown in this figure here and on this figure here have removable discontinuities at C, because we can just go back and redefine the function to make this continuous. We will just have to define f at C to be equal to this point so that this function becomes continuous at that point. And the same also with this one. We can just redefine the function to make it continuous at this point. But in here, on this example or figure here, this is a case wherein the discontinuity is non-removable. So you have a non-removable discontinuity at x equals c in this case, because we can't really do something. We cannot redefine the function at x equals c to make these two equal. Let's consider the following examples. Let's discuss the continuity of each function given here. Letter A, f of x is equal to 1 over x. Now let's look at the domain of the function. We have f of x equal to 1 over x. So the domain is just the set of all real numbers except 0. So the domain is all non-zero real numbers. Now from theorem 1.3, we can conclude that f is continuous at every x value in its domain. So if x is in the domain of a function, then the function is continuous at that point. And so for this function here, the only possible point of discontinuity is the value that is outside of the domain of this function, which is x equals 0. Now, if you look at the graph of the function 1 over x, this is how the graph would look like. We have a non-removable discontinuity at x equals 0, because there's really nothing we can do here to make the function continuous at x equals 0. For the second function, the domain of g is all real numbers except at x equals 1, because the function becomes undefined at x equals 1. Now from theorem 1.3, we can conclude that the function is continuous at every x value in its domain. So the only possible point of this continuity, or the points, the x values that are outside the domain of the given function. At this case, it is x equals 1. Now from the figure here, we see that the graph of this function, g of x equal to x squared minus 1 over x minus 1, is this line here with this hole. So in this example, we have a discontinuity that is removable, meaning we can do something, or we can redefine this function to make it continuous at x equals 1. So by redefining g of 1 as 2, the function becomes continuous for all real numbers. Now for the third function, h of x equal to this piecewise defined function, x plus 1, whenever x is less than or equal to 0, and x squared plus 1, whenever x is greater than 0. As you can see here from the graph of the function, the graph of the domain of H is the set of all real numbers. So the function is defined for all the set of real numbers, and the function is actually continuous from the left at 0. So there's actually no break or hole in this case. So we have a function that is continuous on an entire real number line. Now for the last function, which is y equal to sine of x, the domain of y is the set of all real numbers. And also refer to this theorem 1.6 for the limits of trigonometric functions. As you can see here, we can just use direct substitution method to evaluate the limit of a trigonometric function. Now also, if you recall the graph of y equals sine of x, the graph of y of sine of x would look like this, and it would continue until infinity. It is actually sinusoidal. So this function, y equals sine of x, is continuous on an entire real number line. Next, let's discuss one-sided limits and continuity on a closed interval. To understand continuity on a closed interval, you first need to look at a different type of limit called a one-sided limit. For instance, the limit from the right, or sometimes called the right-hand limit, means that x approaches c from the values greater than c. That means x approaches c from the right of c. And we denote the right-hand limit as this. So the plus sign here is used to denote the right-hand limit. So this one is read as the limit of the function f of x as x approaches c from the right is equal to L. Similarly, the limit from the left, or sometimes called the left-hand limit, means that x approaches c from the values less than c, or the values at the left side of c. And we denote the left-hand limit as this. So the minus sign here is used to denote the limit from the left of c. So this is read as the limit of the function as x approaches c from the left is equal to L. One-sided limits are useful in taking limits of functions involving radicals. For instance, if n is an even integer, the limit of the nth root of x as x approaches 0 from the right is equal to 0. It is useful for taking limits for functions like this, because this is an example of a function whose domain is the set of all real numbers greater than or equal to 0. Example number 2. Find the limit of f of x, which is equal to the square root of 4 minus x squared, as x approaches negative 2 from the right. If you consider the graph of the function, f of x equal to the square root of 4 minus x squared, we actually have a semicircle. Now, if you look at the limit as x approaches 2 from the right, this is this limit here as x approaches negative 2 from the right. So if you look at that one, you see that the y values, or the function values, approaches to 0. The y values approaches to 0. The graph here goes here as x approaches negative 2 from the right. So the limit of the function as x approaches negative 2 from the right is 0. When the limit from the left is not equal to the limit from the right, we say that the limit does not exist. That is what this existence of limit theorem states. If f is a function and c and L are real numbers, the limit of f of x as x approaches c is L if and only if the left-hand limit, the limit of f of x as x approaches c from the left, is equal to L, and the right-hand limit, the limit of f of x as x approaches c from the right, is also equal to L. Now, the concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. Basically, a function is continuous on a closed interval when it is continuous in the interior of the interval, so it is continuous in the open interval, and exhibits one-sided continuity at the endpoints. That is stated formally in this next definition. We say that a function f is continuous on a closed interval ab when f is continuous in the open interval ab and the limit of f of x as x approaches a from the right is equal to f of a, and the limit of f of x as x approaches b from the left is equal to f of b. So that means that if you want to check on continuity on a closed interval AB, first, it should be continuous on the open interval AB. And next, the function must be continuous from the right of A. And also, the function must be continuous from the left of B. Discuss the continuity of the function f of x equal to the square root of 1 minus x squared. First, let's look at the domain of this function here. Now, the domain of this function is the closed interval -1 to 1. You can solve that by getting this expression here, 1 minus x squared, and then make that greater than or equal to 0. And from there, you're able to solve for the domain of that function. Now, first, we are sure that the function is continuous at the open interval -1 to 1 because this is inside the domain of this function. So then the next is to just look at or examine the continuity of the function on the endpoints of the closed interval. Now, if you look at the continuity of the function here at the endpoints of its domain, if you look at the limit of the function as x approaches -1 from the right, you can just use the substitution method. Replace x here by -1. So you have 1 minus 1 that is equal to 0. So, and this is equal to f of -1. Then we say that the function is continuous from the right of -1. And we can actually verify that by looking at the graph of the function of f of x here. Similarly, if you look at the limit of the function on the other endpoint, so if you look at the left-hand limit of the function at x equals 1, you can also use the substitution method and you get the value of 0 here, which is the same value you get when you evaluate the function at x equals 1. From there, we can say that the function is continuous from the left. So therefore, we can conclude that f is continuous on the closed interval -1, 1. Next, we discuss the properties of continuity. Consider this theorem here. If b is a real number and f and g are continuous at x equals c, then the functions listed below are also continuous at c. That means if you multiply a constant to a function that is continuous at c, the product is still continuous at c. If you have two functions continuous at c and you multiply them, Their product is also continuous. And the sum or difference of two continuous functions are also continuous. And also the quotient. The quotient of two functions that are continuous at C is also continuous at C, provided that g of C, this one, is not 0 when x equals C. Now, so far in our discussion, we've seen the following functions are continuous at every point in their domain. These are the polynomial functions, rational functions, the radical functions, and the trigonometric functions. Now, if we combine this with theorem 1.11, we can conclude that there are wide variety of elementary functions that are continuous at every point in their domains. And by theorem 1.11, it follows that each of the functions below is continuous at every point in its domain. So as you can see here, this is just a sum of two functions that are continuous over its domain. And this is a product, a constant, a scalar product of a function and a scalar. The function here is continuous over its domain. And this is also a quotient of two functions that are continuous over its domain. Now, this next theorem here allows us to determine the continuity of composite functions, such as this function and this function. So if G is continuous at C and F is continuous at G at C, then the composite function given by F circle G, or composition of F and G, is also continuous at C. Now let's consider the following functions and determine the intervals for which the function or each function is continuous. We have f of x equal to tangent x, g of x is equal to sine of 1 over x, or the piecewise function sine 1 over x when x is not 0, and 0 when x is equal to 0. And the third is x times sine of 1 over x when x is not 0, and 0 when x is equal to 0. So first, let's consider the first function, f of x equal to tangent x. We know that tangent x is continuous over its domain. Now, let's just go ahead and compute for the domain of tangent x. So we could think of tangent x as sine of x over cosine of x. And that will just be 0 if the denominator is 0. And we know that cosine is 0 if x is a multiple of pi over 2. So that is when x is pi over 2 plus n pi, where n is an integer. And all other points, f is continuous. Now this result can be verified by looking at the graph of tangent x. This is how the graph of tangent x and this continue up to from negative infinity to positive infinity. And as you can see here, the function tangent x is continuous on the open intervals negative 3 pi over 2 to negative pi over 2. So it's actually discontinuous at pi over 2 plus n pi. So at these points here. Now for the second function, which is sine of 1 over x, because y equal to 1 over x is continuous at all points except at x equals 0, and sine function is continuous for all real numbers, real values of x, it follows that this function y equal to sine of 1 over x is continuous at all real values except at 0. Now at x equals 0, the limit of g of x does not exist. So therefore, g is continuous on the intervals negative infinity to 0 and 0 to positive infinity. And you can verify that from the result. So for letter C, the function is x sine of 1 over x. Now this function is similar to the function in part B, except that the oscillations are damped by a factor x. Now, to do this, we will use the squeeze theorem. So using the squeeze theorem, we obtain this. So we know that this expression here is greater than or equal to negative of absolute value of x and less than or equal to the absolute value of x, where x here is not 0. And then using squeeze theorem, if you take the limit as x approaches 0 on this side and on this side, they're both equal to 0. So we therefore conclude that the limit of this function here as x approaches 0 is 0. So therefore, since h of 0 in the definition is also equal to 0, so therefore the function is continuous on the entire number line. And you can actually verify that with on the figure here. So this function, this is the function x sine of 1 over x, and that function is between negative absolute value of x and positive absolute value of x. Now let's turn our discussion to the intermediate value theorem. Theorem 1.13 is an important theorem concerning the behavior of functions that are continuous on closed interval. The intermediate value theorem states that if a function f is continuous on a closed interval ab, and if f of a is equal to f of b, and k is any number between f of a and f of b, then there is at least one number c in the closed interval ab such that f of c is equal to k. The intermediate value theorem tells you that at least one number c exists, but it does not provide a method for finding c. Such theorems are called existence theorem. Now, a proof of this theorem is based on a property of real numbers called completeness. Now, the intermediate value theorem states that for a continuous function f, if x takes on all values between a and b, then f of x must take on all values between f of a and f of b. So as an example of the application of intermediate value theorem, let's consider a person's height. A girl is 5 feet tall on her 13th birthday and 5 feet 2 inches tall on her 14th birthday. Then, for any height h between 5 feet and 5 feet 2 inches, there must have been a time when her height was exactly h. It seems reasonable because human growth is continuous and a person's height does not abruptly change from one value to another. The intermediate value theorem guarantees the existence of at least one number c in the closed interval ab. There may, of course, be more than one number c such that f of c is equal to k, as shown in this figure here. So k is between f of a and f of b. And as we see here, there are 1, 2, 3 values between a and b such that f of this c sub 1 and f of c sub 2 and f of c sub 3 is equal to k. So there are 3 c's such that f of c is equal to k. In this next figure here, this is an example wherein if a function is not continuous on the closed interval ab, then the intermediate value theorem will not apply. Now in this graph here, the function jumps over the horizontal line y equals k. And so therefore, this k here is between f of a and f of b. And as you could see here, there is no value c in the closed interval ab such that f of c is equal to k. Another use also for the intermediate value theorem is to locate the zeros of a function that is continuous on the closed interval. Specifically, if f is continuous on the closed interval ab and f of a and f of b differ in sign, then the intermediate value theorem guarantees the existence of at least one zero in the closed interval ab. So to illustrate, we will look at this example here. We will use the intermediate value theorem to show that the polynomial function f of x equal to x cubed plus 2x minus 1 has a zero in the interval 0, 1. First, let's take note that the function is continuous on the closed interval 0, 1 because the polynomial function is continuous in the set of all real numbers. 0, 1, this closed interval 0, 1 is a subset of the set of all real numbers. So f is continuous on the closed interval 0, 1. And because f of 0, so then we will evaluate this function on the endpoints of the closed interval. F at 0 is just equal to -1. Just replace this x here by 0 and we get -1. Also, f of 1, if x is equal to 1, you replace x here by 1, we have 1 cubed plus 2 times 1 minus 1, and that is equal to 2. Now, you can verify this one is a negative number, so f of 0 is negative, and f of 1 is greater than 0, so that means they differ in sign. Then it guarantees that there is a 0 on that closed interval. And you can therefore apply the intermediate value theorem to conclude that there must be some c on this closed interval 0, 1 such that f of c is 0. Well, because 0 is between -1 and -2. So 0, when you say 0, the y value is 0, and that is between -1 and -2. So by intermediate value theorem, we know that there is a 0, there is a c such that f of c is equal to 0.